Just need the display, I guess. Yeah, for sure.
Oh, I have another one.
Okay, cool, cool, awesome. Hey, Sia, good to see you. Good to see you guys. Thanks for coming. Paula, nice to see you. Nice to see you. Don't worry about it. Yeah, sure. Oh, that would be nice. Yeah, sure.
Listo, listo. Ok, muy bien. No veo. ¿Dónde estoy? ¿Por qué no me veo? Acá. Ah. No. Sí. No, es que está la... Ajá, tenemos cámara y todo. Ah. No, no tanto. Ok, listo. Por acá. Infinito. Hola, buenas noches. Bienvenidos a Hacker Garage de nuevo. Hoy es una noche especial porque logramos revivir el YouTube. Entonces, a ver cómo nos va con la transmisión en vivo. Es la primera vez, pero fue muy importante para nosotros lograr hacer esta transmisión con esta comunidad naciente que es Embedded Systems. Así que, pues nada más darles una pequeña introducción para quienes es la primera vez que vienen. El Hacker Garage es un espacio público abierto a cualquier persona que quiera venir, trabajar, colaborar, usar el espacio como quieran. Nos movemos a través de membresías mensuales. Es un lugar donde, si tú tienes tu membresía, de alguna manera puedes usar el espacio como tú quieras. Puedes usar las máquinas, las herramientas, venir a hacer coworking, colaborar con los demás miembros, venir a las noches de juegos de mesa. Bueno, las noches de juegos de mesa son completamente libres, así que… pero bueno, en realidad es una comunidad de hackers, de creadores, de personas que están interesadas en compartir ideas, en trabajar y hacer un montón de cosas. Así que, bienvenidos, welcome. I'm going to switch to English now because this community has a German leader. And so most of the things that we do in this community, we do it in English. So we have a couple of people from other countries, so we want to have everyone included. So welcome, Fram. I'm going to introduce you a little bit. So he's the leader of this community. Embedded Systems is a new born community here in Hacker Garage. So I'm going to leave you with him, and welcome.
Thank you so much. I just want to check this is working. Good. I just put this back, and I would probably need my screen to be projected as well. So I can maybe, sorry, I just need to put this one back. Wow, there's a lot of stuff there. It's quite difficult to find the right screen here, but I think it's this one. I2C basics. Okay, thank you everyone for coming. This is our next social for embedded systems. And yeah, I will say a bit more about the community maybe after the break, but I'm really glad that we have such a good community, so many attendants coming to our socials. And I'm trying my best also to get sponsorship and funding. It's not so easy. So we're trying with various companies to get some sponsorship. We have a space now on GitHub where you can collaborate and where you can also raise issues and questions. You can propose things. So that space exists, and I really encourage you to use it. So I will put some links in the second half. And today I'm going to show some code which already exists on that space. So, and you can play around with the code, you can extend it. It's really open. I don't want to take ownership of any of those experiments in code, so we can really make this a joint effort. So just something about myself a bit. I mean, I've already talked about this before. So I work in both academia and in industry as well. I'm a freelance consultant for rigorous engineering of safety critical and security critical systems. I work in software, hardware, many different levels, but mostly in the area of model-based engineering. So I'm trying to use engineering techniques for which we can show that we actually know in the end that the system does what it is expected to do. I'm also taught at university, published papers about this kind of area. And yes, since 2 years I'm living in Mexico with my wife, and we are very much enjoying it here, both the people, the work. Great. So what is this talk about? Introduction. So the topic is to talk about I2C, and I think it's pronounced I2C. I2C is a very common thing you find in embedded systems. It's a communication protocol and a bus standard. So whenever you're connecting something to an embedded device, you will probably come across I2C as a way to connect this device or connecting your chips in some way. Many devices and chips use I2C, as I said. It's a very flexible protocol that supports multiple masters and multiple slaves. So you can have many people sending and many people receiving at the same time, which adds, of course, to the flexibility of it. It comes with some constraints and ramifications that we need to understand. And this talk is not so much about how to use it. So the second talk, so we have Carlos Arias here, who's going to explain something. Pepe might also show us a little bit about logic analysis. Yes, there will be some more practical parts in the second half of the talk. Many boards, like Arduino and so on, support I2C natively. That means you can, almost without any effort, plug in any I2C device. You don't need to basically write a lot of code to get something working. But what I have to say is that these devices are not always fully compliant. That means they cannot explore all the possibilities of the protocol. For instance, what happens if you have multiple masters? People can talk at the same time, and you need arbitration to make sure that you're resolving conflicts and so on. So there are some things which you need to be very aware of if you're using a particular protocol or driver. So here's an overview. Learn a bit more about the history of I2C, some technical details, and physical design, so looking at the physical protocol layer, looking at the data exchange and actually the data that gets sent and received in I2C. Then we will also look at some typical devices, and lastly, controlling devices with microcontrollers. So this is maybe where it gets more interesting if you want to actually have a device that you want to control, and want to say something about that as well. So we won't go into much detail, as I say, on a concrete example here, but this will be the second part of the talk. History. Well, as far as I understood, was developed by Philips Semiconductors, which I think knows NXP, or at least, I mean, NXP was a spin-off, I guess, of Philips. I'm not sure to what extent Philips still exists and what the relationship is now. The motivation was to attach low-speed peripherals, ICs, to processors and microcontrollers. And that was the design that they wanted to take with this. So it's not about connecting USB devices, it's really connecting things on the same chip, where you have very small distances between wires, you have maybe multiple components you want to support. It's not a registered trademark since November 1914, so the only thing that's trademarked is, I think, actually that logo there. And so there's, you know, you can use it freely, don't have to pay royalties or anything. The I2C goes under different names. So this actually should not be TMI, but TWI, which M turned around, which is the two-wire interface of Atmel Arduino. And also you find it in other places, like display drivers, for instance, or display connections. They use that. It's this VESA interface. There's another typo there, anyway. And also for power control and systems control. And there's another modern version, I3C. And I explain a bit later what the motivation is behind that one. Why do you want to have a modern version of I2C, and call it I2C. So that is the features. So when we look generally at protocols to interact, it helps sometimes to see what possible ways you have designing these things. And these are just a few. These are not all of them, but I think these are ones which I think are probably important. One thing is, how many wires do you need to connect things? Last time, Pepe showed us how to connect stuff with UART, and we only needed one wire. So it was very simple to do that. In I2C, we have 2 wires, but we need to know that because that affects also things. We need to know some physical characteristics, so what voltage levels can be supported. And these 2 things, capacitance and maximum load, are very important with this protocol. And I show this a bit later, but this is also things we need to know. Some protocols are asynchronous, self-clocking, in a way that you can just send data, you don't need a clock. And the receiver will make sense of the data. It can just create its own clock. So there's usually some PLL, which is a PLL. Anyone heard about PLLs? It's, yes, Pepe. Yes. So phase lock loop is a device that's sometimes used to generate clocks, basically, or to also to kind of divide or adjust signal phases and clocks. We have also serial versus parallel. These used to be more popular, I think, probably maybe in the 80s. Nowadays, serial is becoming so fast, I'm not sure that there's still so much parallel protocols used. An important thing is also that we can have digital versus modulated signals. Modulation means you're using analog features, which I think, Carlos, you're probably very familiar with QM and all these kind of modulation things. And you can transmit more data using this modulation, but it makes the decoding a bit more difficult. Transfer rates are important. How much can you transfer? How fast can you transfer? Can you have multiple senders in the same bus? And can you have multiple receivers as well? And lastly, characteristics such as noise sensitivity or error characteristics. And there's a few protocols on the right-hand side, which hopefully we're going to look at. So I want to look at VGA at some point, so which is very interesting because it's a mixture of digital and analog. Sync signals are digital. The pixel, the color signals are analog. And it's, in this case, it's asynchronous in a sense, so it's self-clocking. It doesn't have an explicit clock. And yeah, there's a lot of other things we can look at. But today, it's I2C. So here are basically the details of I2C. We have 2 wires, SDA, SCL. And when we have a controller and a peripheral, we're just connecting SDA to SDA and SCL to SCL. So it's not like UART. UART was the other way around. We have to connect RX to TX and crossing them over. Now here, they're just connected on the same bus. So just remember that when you later try things out. We can have multiple masters, multiple slaves, which is very cool. So we have just one bus, but we can have different things on the bus. It's a serial data transfer. And this transfer rate, usually the standard rate is about 100 kilobits per second. So roughly about 10 kilobytes per second. And it also has a fast mode, which is 400 kilobits per second. Now, there are variants of this protocol that go up to 1 megabit, even 5 megabit. But there are some constraints with these variants, and you can use them, but you need to be aware of the constraints that come with this. It's designed for short distance, and that means also the capacitance of the connection on the bus shouldn't be more than 400 picofarad. This is important. I explain later why, but it's an important factor of the design of this protocol. Since we have multiple masters, we need to resolve conflicts on the bus. And there's also a way to do that, which I'm going to explain a bit later. And the interesting thing is that slaves can slow the clock down. So if you have slaves, and the clock goes too fast for them, not every slave you have might support this 400 kilobits, so they can slow the clock down if they want to. And it's not quite trivial to support this at the hardware and software side. It's not difficult, but it's more difficult than UART, I would say. You need a more sophisticated logic that actually does that. So that's basically what the protocol is. So how does it work? Assume we have two controllers. One controller wants to send data on this line, and another controller also wants to send data on this line. So we have 5 volts and 0 volts. Now, if that happens at the same time, what's going to happen? Short circuit, exactly. So we're getting like a short circuit. So that's not good. So how do we solve that problem? I mean, we cannot basically, if we want to connect everyone to SDA, we cannot allow everyone to just put anything on the bus. So the way that I2C solved this is to using something called an open drain circuit. So basically that means that the controller can output a 0, never a 1. Ones are not allowed. Only zeros are allowed. How do we get a 1? We have 2 resistors here. And the resistors are connected to the power supply. So because these resistors are usually quite high, so they are in the range, I would say 2K to 5K, maybe even 10K. I think about 5K, 2K to 5K usually. You wouldn't have a lot of current flowing through them. So even if someone puts 5 volts on here, if you put a 5 volt, we don't have a problem. But if you put a 0 volt, the current will flow through the resistor, but it's not quite a short circuit. So it's a low amount of current. And in that way, you can always put a 0 on the bus, and you put a 1 by not putting anything. So if nobody talks, nobody sends anything on these 2 lines, either the clock or the data, we're getting a 1. If someone starts talking, we're getting a 0. And that's basically how many, let's say, many senders can talk on the same bus. That, of course, restricts how we can do communication, but that's an important design principle of I2C. So just to say some implication, to tell you some implication of this. First of all, everybody can talk at the same time by pulling it down to 0. But the masters must detect if somebody else sends at the same time. That's the issue, because you might have someone wants to put a 0, someone else also wants to put a 0. So they cannot just send, they have to read at the same time. They have to see, oh, I'm just sending a 0, or I haven't sent a 0, I want to send a 1. Now sending a 1 means basically outputting nothing, but they need to detect if somebody else sends a 0. And that is a kind of thing that the masters have to do to figure out if there's a clash. And if they realize there's a clash, and if they realize what I'm doing is not consistent anymore with my observations of what's happening, I need to withdraw. And this is not a problem, because usually, if you have 2 parties, only one will withdraw. One will see a consistent image of what's happening, the other one will see an image which is not consistent based on his observations. And this is how arbitration works in I2C. The first one who sees, well, I want to output a 1, but I see a 0. Okay, cool, someone else is sending. I'm going to withdraw. And nobody even noticed that I have been sending, because there's only one person who has been sending and has seen the consistent signals, and he's still going to continue. He doesn't even know about me. So an important thing is that voltage changes can be slowed down. And I show this on the next slide a bit. But this is a thing that we need to consider in terms of speed. So you can only send so fast, because voltage is not going to change instantly. And people showed last time with the sampling that in the real world, nothing happens instantaneous. Everything goes in slides, slopes, up and down. Sometimes you have oscillation even. Nothing is really clear and not so crisp in the analog world. And this depends on a couple of issues that we're going to explain. And I hope, if we have a chance in the second talk, to reproduce that with the logic analyzer, if you have it. I'm not sure it's going to work on these small systems, but if someone has a very long wire, maybe we can try it and see if that actually works. The masters also need to sync on the same clock rate. And the way that works is usually that if the clock goes down, he might hold it a bit longer for everyone else. And everyone has a chance to slow down. It's like you're sitting in some kind of classroom and everyone can say, no, this is too fast, I want to slow down. So they have to adapt to the slowest participant. Requires also protocol. And now if you think, this sounds complicated, it actually is. So, I mean, and you see this when you read data sheets of microcontrollers that implement that protocol, and they tell you exactly what they do implement, what they don't. And still then you have an issue if you have too many people sending on the bus. So it's not trivial when you have push it to its limits. So let's look a little bit more what open drain means. So assume this is our SDA or SCL line. We will have a pull-up resistor to 5 volts. That means we will observe a 1 here if nobody sends. In fact, it will be almost 5 volts. If you don't put any load on the bus, you get a voltage divider here that tells you almost that you've got 5 volts on the bus. And you should never, pull much current from that bus, because otherwise you're going to get in trouble with your resistor. Now, if you want to set a 0, you have a capacitor that, not a capacitor, some kind of transistor that closes. And when it closes, the voltage goes from 5 to 0. That can happen very quickly, depending on how quickly the current can flow through here. If it is a very low resistor here, it can happen quite quickly. But you need to imagine the wire is like a piece of metal. It has capacitance, it has charge. Now, if I withdraw the 0, and now I'm creating again a 1, that means that the charge that you have here needs to be, or the wire, if it doesn't have charge, actually when it's 0, it doesn't have charge, when it builds up a charge, that needs to happen through this resistor. And the current flow is limited through the resistor. So if you connect this directly to VCC, it will charge very quickly. But here, it will take some time for this wire that you have here, which is modeled by this capacitor, to charge. So what you see is not that. What you see could be more like that. So you have a fairly quick transition from 1 to 0, but then to overcome the capacitance of your connection, it takes a while. And maybe your logic will realize at some point here that it becomes a 1. It depends. And this is the implication of having this kind of circuit, that you don't have signal changes immediately. And we are just talking about wires, but wires have electrical properties. They're not just negligible. And if you do circuit design, layout design, you also find that you need to be careful. How thick is your wire going to be? Are there other consumers that also have some impedance of their own and introduce some capacitance maybe into the bus? So the real world is more like that. And that limits the speed. Because if I squash this diagram, I will find suddenly that I don't have enough time for the signal to become 1. And that's why the speed limits of I2C basically come from. You can do some tricks to overcome this problem. Either by using a lower resistor, or you're using very small wires maybe. I don't know, I'm not an expert. But I think you always hit on some kind of compromise, especially if you have situations where you have multiple masters and slaves. So that is the electronics designers who need to consider that. So this is the physical part. The actual logical part of the protocol is the data that you're transmitting. So how do we communicate on these two wires, SDL and SCL? Now, there's 2 important things you need to do. You need to send a start condition when you want to send, and you need to send a stop condition when you're finished. When you look at this clock signal, it alternates between 1 and 0, 1, 0, so it gives you like a clock. A start condition can only be issued when the clock is 1. So when the clock is 1, you're pulling down the data line, says you're going to start transmitting. If the clock is 1, you're pulling up the data line, means you're going to stop transmitting data. Now, when you look very carefully, when these data here changes, it only changes when the clock is 0. So as a rule, the data can change when the clock is 0. The start and stop condition can happen when the clock is 1. And that's basically all you need to know about how this protocol works. There's also something called a restart condition. And this is when you want to immediately send afterwards, and you want to give the bus to someone else. So instead of sending a stop condition, you can actually send a restart condition, and then you can keep control of the bus and not giving it to someone else. So once you have your start condition, you're sending basically your data bits. The most significant first and the least significant last. The first thing you're sending is an address. So these displays, if you look at the small ones I brought, they have a hex code on the backside. That's the address. Now, the address is only 7 bits, which gives you not so many possible devices, 127. So this is a weakness of I2C. It only has 127 addressable devices. There's a 10-bit format of this, so there's a not so much used format where you can extend this to 10 bits, but it's quite common that these things clash. So sometimes you can control this. They have jumpers, or they have some sort of soldering bridges that you can kind of remove, but you can run into issues due to these clashes. The first one here, the RV, the last bit, tells you if you want to read or write. So if this you can control to have either reading or writing transactions. And what happens afterwards really depends on the device. So this could either be data sent from the master to the slave, or this could be data sent from the slave to the master. And they're using the same line. So because of the open drain circuit, everyone can send, also the slaves. So even the slaves can output data on this one. And if I have a writing transaction, then the first thing I would usually send is some kind of command. I mean, it depends what your device is, but you will send, for instance, I want to send an address that I want to write to, and then you can have more of these data where you're actually saying the data that's written. This last bit here, bit number 9, is an acknowledgement. And if the master sends, the slave will use this to tell the master that he has received the data. If the slave sends, the master will tell the slave that he has received the data. So this is a kind of error detection mechanism. And the acknowledgement happens basically after each time you send 8 bits. That means, effectively, you don't have a bit rate of 8 bits per 8 clock cycles. So you need to take into account that the actual transmission speed, depending on the speed of the protocol you're using, is maybe a bit less than that, because you always have this acknowledged bit that you need to also consider. So essentially, this is basically how the protocol works. I mean, at a higher level, you kind of have your start condition. You're sending either 7 or 10 bits for the address. You're sending the read-write bit. Then the acknowledgement is sent either from the master or the slave, whoever needs to acknowledge. Then you have a data frame, 8 bits, another data frame, and you can have many data frames. So if, for instance, I'm sending some data to a display like this, I could send the whole data for the screen. I can send data frames until the whole screen is filled. And in the end, you send a stop condition. So this is quite nice. It's very simple. Doesn't really explain very much what kind of data you need to send, but you need to look at the data sheets to actually know that. And the data frames, of course, can be master to slave or slave to master. So usually what you have sometimes is that you have a data frame here that tells whether you want to, well, here you say you want to read or write. Here you send the data frame then maybe to give an address, and then this might be a read frame. And it depends on the device. My impression, I mean, I'm not an expert, my impression is that every device does it in a different way. And there's a few guidelines how you should do this transaction, but I'm not sure if they're always strictly obeyed and written down. So there's a few perks. As I said, masters can restart, and that means keep control of the bus. We have the acknowledgement, which I've already explained. The important thing is that you can also stretch the clock. So a slave, if you go back, a master might say, I want to read some data. And the slave has to reply. But maybe the data is not ready. So what the slave can do is keep the clock down and wait until the data is ready. So the slave has the possibility to slow down the master by keeping the clock down. And there's actually no lower limit as far as I understood. I mean, there's something like 10 kilohertz, I think I read somewhere, but you can really, you can keep this down and stop the whole thing from working. So which makes it also difficult when you implement a multi-master, multi-slave system. It might just deadlock because someone is holding the signal down. Some devices you can control, actually, which address to use. I mean, this is a device, you might have some sort of connections there that you can set to control the address, to avoid clashes. Since masters compete for the bus, you can end up with bandwidth issues. So if too many people send at the same time, it doesn't mean that the system is not going to work. It just means that someone never might get access to the bus. So if you have an analog-digital converter and you want to constantly sample data, could be an issue. And the actual communication API, so the command interface, that's not really described very much by the protocol. And just to try to show you how this looks like, I can maybe try and open this. So the chip that we're going to look has a data sheet. And this is a data sheet. And I just see if I can make this a little bit bigger. So we can, let's say, maybe 150, maybe 200 even. I hope that's just about readable. You can make this a bit bigger as well. And usually you have data sheets that tell you how the interaction works. And even for this small display, there's quite a lot of here. I just see if I can find the part which is the interesting one. So there's a lot of information here, basically. Let's just see which section could be interesting. So we have graphics, display, RAM. No, this is just general stuff. Yeah, so here's the command description. And this basically tells you, if I go a bit further, yeah, this is still not what I'm looking for. Yeah, I can see you need to find your way around here. So there's a lot of information, even for such a small device. Let me see if I probably went past it. Yes. Yes, this is a command table. So for instance, you find commands here for scrolling. And this basically tells you the kind of bytes you need to send to the device so to make the screen scroll. And there's different kinds of commands. I mean, you have also commands here which are to set the contrast of the display. You can switch the display on and off. You can invert the display. And this is where we're going to look to find out which data, what commands to send to the display to do that. Okay. So let's go back to this one. Great. So here's a few typical devices that you might find for I2C. You have sensors for temperature, humidity, pressure, acceleration, memory modules, usually small ones, but I mean, these modules, for instance, give you some EEPROM, some non-volatile memory if you want to connect your Arduino to some memory. I mean, Arduinos have that as well, but I'm not sure how much they have. I think it's just 1K or something like that. Audio devices, digital analog converters, and the other way around. Real-time clocks. Also, you can use I2C devices to expand your inputs and outputs. So you might have a device which gives you more inputs and outputs. And as I said, there's some special modules for power management or systems management. These are all common applications. And the one we're going to look is mostly this one right now. Well, not right now, but in the next talk. So now that you know what I2C is, and why am I telling you all of this, is really that when you're using a protocol, sometimes it is useful to know its limits. What can it do? What can't it do? Why I'm not seeing anything on my display, for instance. So to debug this is not always easy, unless you're using one of those logic analyzers, which are not cheap, but that could help you. But it's important sometimes to know how protocol, even at the physical level, work before you're connecting them. Otherwise, you might even damage your device because you forgot that you need a resistor there. You cannot just connect things like that. So here is your network of components. You have a master. In this case, the master is your Arduino. And the Arduino has a clock and a data signal. Now, some boards have actually 2 I2C channels, as I understood. So this is the one I'm using on this device, and I think this one actually, the Uno only has 1 of them. But I think there's actually also devices that give you more than 1 channel. So one thing you don't need to do is pull up resistors, because the chip already has them inside. So every output, in fact, of an Arduino can be a pull-up resistor. So you can attach this directly to any output that you want. So here's a simple setup that I'm using for the demonstration. So you have your device here, and these 2 wires here, the white and the blue, I'm using for the data and the clock, and then you're just connecting the power. So it couldn't be any easier. You don't need any additional components, no resistors, nothing. Just connect your display to the Arduino, and that should work. Some Arduinos, I think, also contain markings for the output. The thing is, you can only use fixed pins. Yeah? Yeah. So that's a good question. Which is the master and which is the slave? So the Arduino will be the master, and this one will be the slave. So the display is not sending anything itself. It's not even going to reply to you. It could reply to you potentially, but it doesn't. It's not fully, I think in I2C it doesn't actually fully implement, so you cannot read out the memory. Use the correct pins, so don't confuse them. Don't confuse these 2. So that happened to me once, and it was a bit smelly, but it didn't break the system. And you need to make a note of the device address. So the first time I tried this, it was a very frustrating experience because I couldn't get anything displayed. And then I realized that the address that I used was the wrong address. And there's a few other things you need to consider when you do this, but it might not work out of the box. So the display sometimes has some markings. For instance, this one has got 2 addresses here on the back side. And there could either be 7-bit or 8-bit. As I said, 1 bit is used for our reading, writing. So sometimes you might need to even multiply this by 2, maybe. But yeah, it gives you some information about this, what the address of the device is. And you find that usually from the provider that you bought it from. So the last part of the talk, I just want to say a bit more how chips support I2C. Now, I2C, as we see, is not such a trivial thing to implement. So chips have inbuilt support for that. They help you a little bit. So you don't have to implement the protocol from scratch. They already have some circuitry which makes certain things easier. And usually what they have is some features where you don't have to bit bang. So bit banging is a term which is often used when you generate signals in a very low-level way, where you just output a 0 or 1 to some hardware address to getting your signal to move from 0 to 1. Now, this is very slow because your CPU takes a lot of effort doing that. I mean, if you have transitions between bits, or between these 2 clock lines or this SDA, and every time you need to change, you output some data from your CPU just to change the level of these. It takes most of the time of your CPU to do that. So instead, they're having some internal hardware that allows you just to say, output me that value. And then the whole protocol that we've seen before, with the start condition, the stop condition, sending the data, checking the acknowledgement, all of this is done by the control unit of the microcontroller. And it doesn't mean that your software doesn't have to do anything. It still has to do that, but you kind of trading bit banging, what I would say is byte banging. So you're just putting the bytes out, and you're doing that whenever you need to, and the control logic does the rest. Now, one important thing is to consider timing here as well, and I'll say a bit more about that, because what seems a small time might not actually be such a small time. You always need to compare times. A microprocessor running at 100 megahertz, 10 kilohertz is an eternity. You don't want to waste 10 kilohertz. You can do a lot of stuff in that, so you need to kind of relatively compare the timings. But as I said, the microcontrollers usually support some of that for you. And if you take a look, let's say, at the data sheet of the Atmega, which is the microcontroller used in the Arduinos, you find, if I can find the, let me see the, I'm already past, no, this is already a little bit past. I just want to look at the contents page. I think it's chapter 21. Yes, yeah, TWI. Now, it's not trivial even how these microcontrollers support those protocols. They give you a bit of explanation here, but then you find a lot of text and a lot of documentation, some signal graphs, and then at some point they will give you all the hardware registers. So this is the stuff you would need to read if you implement a driver. Even they tell you the low-level assembly you should use for certain things. So the guys who implement these drivers, they have to read this document, and they need to understand every little bit. You make one mistake, you're shipping this maybe to, I don't know, your community or your clients, and they will find it, don't worry. So it is very important to know in particular, I mean, this is the assembly, this is the C, and sometimes even the amount of time an instruction takes is important because you need to count the cycles. You need to make sure that you're within the timing constraints of your data sheets. And proving that is hard. It's not trivial to do that. But the good news is you don't have to do it because the library, the wire library of Arduino already supports that. So that's not necessary. So it's just to show you that, let me just go back to the slides. And, that there's a lot of stuff behind this. Even the simplest microcontroller, there's a lot of logic and a lot of things you need to know to interface with that. And it's a good exercise to write this, to learn. In practice, you probably wouldn't do that. You would just use something ready-made. But I would encourage everyone, doing this, you really get an appreciation of embedded development. And you see the difference to normal software engineering. Now, this is a driver that I published on the ESG side, and this is how we want to interact with these systems. We connect it, and then we include some library. Now, the setup method, as you remember, is only called once for the Arduino. You want to initialize it, and then you clear the screen. This init is very important. So these displays are not doing anything at all when you connect it. Even you send it data, they don't do anything at all. So you need to send it a certain sequence for initialization to get them to do something. And the most important thing is that you're running this at 5 volts, but it requires 7 volts. How does it do that? There's a certain circuit, it's called a charge pump. And it's basically a mixture of an oscillator and a capacitor. And if you don't activate that circuit using the protocol, the display doesn't get enough, the right kind of level of voltage, I suppose. It doesn't display anything. And you don't find this out easily. I mean, it took me like maybe an afternoon to figure out that I need to activate the charge pump because the voltage was too low. But as I said, I will later show a little bit more about how this driver works. It's not very complicated, but this is how you want to interact with your components. You want to move your cursor, you want to print a string, you want to move your cursor again, you want to print another string, and here just wait forever. So a driver has always different levels, and I will say a bit more later about that. But all of these functions here are custom driver functions, and anyone who knows about Arduino maybe knows what that is. Any idea what that does? So this is not C. This is something else. It's an attribute that you're applying. And it basically tells the Arduino to put this not into RAM, but into program memory. And that's why I'm using different functions here. But again, this is just something to be more economic with space. And here's a quick example of 2 drivers. Let me see if I can show this. So this one is the one from Adafruit. And let's see if I can make this a bit bigger. Yes, I think that works. And the code is not so important. This is just a simple example. And it's a driver you can download. It's a standard Arduino driver from Adafruit. Let me compile this. And I will see if I can activate the camera and show it to you. I think it's this FaceTime, right? And I'll just try to upload it. This is just compiling it, just 1 second. And I just compile the sketch. And it's uploading it. And yes. So this is basically what this little piece of code does. It's quite fancy, isn't it? It's just drawing some lines, and then it's doing something else. And you can see you can write games with these displays, so they do have the capability to do that. They can do graphics. And I don't know what, I think at some point it will just decide that it has done enough and just present, just show some. This is characters. Oh, yeah. Great. But if you look at how much this code actually uses, you have 64% of your program, of your 32K. It's quite a lot. This one, I was very confused. 527 bytes of RAM. Why? Now, the display has 128 times 64 pixels. And I was thinking that in order to do the graphics, you needed a frame buffer. So you need to have some memory to back up basically what you see on the screen before you send it. And the reason you need a frame buffer to do graphics is you can't read the display out, and you can only send it in 8 bits. So I cannot send individual pixels to the display. I can only send 8 of them. But if I don't know what's been there before, I'm always going to overwrite stuff, which makes it basically impossible to do graphics. So why does it only use 500 bytes? It would need at least 1 kilobyte for the frame buffer. The reason is it's cheating. It doesn't use 500 bytes. It uses malloc. So if you basically look at the code of this, we just now I can show this. I probably show this in another demonstration, maybe not here, because I have too much stuff open here. But just trust me, if you look at the code, you find some malloc. This is an interesting one, because I think on a small embedded device with only 2K of RAM, I would never even dream about using malloc, because you don't know how much memory you're allocating. And what is the problem with malloc? I mean, I could also allocate things statically. I could just introduce a static variable there and allocate it. But if I run out of memory, the linker's going to tell me. And I can have a linker script even that tells me I want to have a certain amount of stack space. If I use malloc, I cannot tell this statically. I can only find it out dynamically, which is why I would not use malloc on a system like that, because you don't know if you're going to run out of memory. And if you're unlucky, it might still succeed, but only leaves you 100 bytes of stack space. And I'm not sure if Arduino actually inside its linker script has any constraints on how much stack space you want. And surely the compiler is not going to tell you if you do this. So just keep this in mind. So we have version number 1. And this is another version, which is a driver that I just showed you. And if I compile this one here, now we're using 4K of memory. Most of it is actually the driver from Arduino. It's not this code. This code is just a few hundred bytes, not even that probably, maybe 100 or 200 bytes, maybe. But the 4K comes from the TWI interface from Arduino, because that also needs space. In terms of variables, 225 bytes. And this is true. There's no malloc there. This is actually only the space it needs. So if you just want to print out a simple text message onto the screen, you don't need all this overhead of the driver. So that's why I'm saying you need to consider what you actually need, what are your requirements are, and not just go for any driver you find. Because this uses much less of your memory. It uses, and the RAM that you're using here is essentially your buffer. Because I2C, the way you implement is you want to have a buffer where you can maybe have 32 bytes initialized, and then you send it off, and then you don't care about it anymore until it needs more data. So I'm almost done now with the first talk. Let's just see if I can go back to my slides. And these principles, by the way, they apply not just to I2C, Oh, this is the wrong slides here. Let me just close this one. This one as well. There's too many things here. Maybe I should just go. Yeah. Yeah, and too many slides. Too much stuff here. Yeah, and just go to here. Yep. So now you know what I2C is. You know some of the implications of using drivers, maybe not all the details. And here's a few pros and cons. As I said, this protocol is supported by many devices. It's an industry standard, goes back to the 80s. You find it probably everywhere still, even though it's a bit outdated. It's very flexible, it can have multiple masters, multiple slaves. Most microcontrollers support it natively. I don't think there's many microcontrollers where you have to bit bang it. You could bit bang it, might be interesting. This might not even be so difficult, but I wouldn't do it if you have this support. The cons are limits of transfer speed, distance, connections on a single bus. I2C has a mode where it goes up to 5 megabits, but that means you don't have an open drain anymore. And in this case, I think also they cannot acknowledge the reply because that's a bit tricky. I mean, there's something you can replace this open drain by something like an active pull-up. I don't know how that works. Maybe people here have heard of that, but there's other mechanisms you can use. And of course, you have these issues about contention on the bus. You need some arbitration. And the arbitration here is very simple. There's no randomization. It's not like, I think some protocols like Ethernet, they have more sophisticated ways to do that, or wireless. But here it's very simple. And devices might not always be compliant. So expect you might have some device which doesn't actually speak the protocol in the way that you should. So this is just a summary of what we did. It's not a bad idea as a self-study to write your own driver. I've done this for FPGAs, I've done it for a Neo SoC, I've done it for Arduinos, and I'm always using the same system because I know the system already, I don't waste time understanding it. So it's not a bad exercise to do that. In practical times, this is not required, but we can collaborate on this driver if you think it's useful. There's probably also open source drivers to do that. And this driver could still be useful, I think, to write a game even. I convinced myself you can write a game with this if you don't have overlapping sprites. So if you have a Pong game, it works because you never have overlapping sprites. Mario wouldn't work because you have a play field and you'd probably need a frame buffer to do that effectively. Some further reading. You can look at the specification, which is a little bit boring, but I think this one is quite readable, actually. The Atmega data sheet, don't look at it, but just quickly get an appreciation of how elaborate these things are. There's a nice guide from Texas Instruments, which you can also have a look at. And just to use it, as I said, we have the wire library of Arduino, and we have the integrated, the Arduino documents, which also explain about the I2C protocol. So I think that's as much as I want to bombard you with in terms of information. It might be a bit too much information. So first of all, question time. Do you have any questions? Anything that you find that I didn't answer or that you would like to know a bit more about? Go for it, yeah? Yeah. Yes.
So that capacitance is also, does it limit the number of devices that we can connect on a single bus?
I think it does, but it depends on the properties of these devices. If none of these devices would draw any current, I think you can have more, or it shouldn't limit it. But I think, Pepe, I don't know if you agree, devices, they always have a characteristic, right?
One thing is sharing the data line and the clock line, and another different thing is sharing the power lines, right? So it's totally different. If you have enough amount of current on the power lines, you can drive 127 devices out of each I2C, peripheral, right? But most of the MCUs that I'm seeing not only have ones, they normally have like 4 or 5 or 3, right? Because nobody actually, connect 127 I2C devices to a single bus. Everybody prefer to connect like 2, 3, the most I'm seeing is 4, and they just separate, different buses because since it's an open drain stuff, you can connect, to the same microcontroller, you can connect different voltages as well, right? So you can have like one I2C running at 1.8 volt, the other one running at 3.3, and if the architecture allows, you can have another one running at 5 volts.
So yeah, I think that's a really good point. So you don't need to connect everything to one bus. There are actually components who split the bus for you. And yeah, so there's some ways around it. And usually you have, yeah, as I said, just a few devices, usually just one. I mean, often it's just one device that you need.
Another thing that is really important is that Frank was mentioning that there's some compatibility issues all the time. And one of the biggest constraints all the time is that if you're going to be connecting a temperature sensor and a memory, and one of the two doesn't allow you to have clock stretching, you better separate them to a single I2C bus, because if you connect one device to another one that doesn't support I2C's clock stretching, it will just mess up the entire bus. And what you need to do is actually just go and manually reset every single device on the bus in order to make it work again. So it can be a totally mess. That's the difficulty of I2C.
That's good to hear, because I suspected that. I
Yeah.
never had to face such a mess, but
That
I think
happens very often. That happens very often.
exists. So and why is that? Because it's so flexible.
Yes.
And because devices are small and tiny, they don't support all of that. But yeah, it's a really good point, I think, to bear in mind.
Yeah. And
So does it answer your question? Good. Anyone else? Yeah, go for it, David. Oh, Mike.
Okay, so there's read mode and write mode. I don't think you showed if something wants to like send and then receive, does it send some frames to a stop bit and then send a new start and go in read mode, or is that what the reset command you were talking about was?
This is a little bit where my knowledge kind of stops. I wouldn't say stops, but what I read is different things. I think the I2C standard says that, first of all, you need to send the address, and that's definite. You cannot get around that. The second thing is, let's say you read from a memory. You might also give some more data, which data you want to read. Like an analog-digital converter, you don't have to do that because you're just sampling. But with a memory, you might have to send another data byte or two. And then you can assume that afterwards, the next byte you're going to read. Now, whether you can keep sending on the bus, I think is kind of device specific. Some devices have a continuation mode. Like this display, the second byte you send, you can define whether you want to send in continuation mode. And that means that you send only one command and you just keep sending data. But sometimes data have specific starts and ends. And if the device supports a restart, you can probably just do a restart and you can just continue. And I don't think even you can address another device. Restart is not sending to the same device. It's just you keep control of the bus. But I think this is probably device specific. I don't think I2C wants to make very strong assumptions about it. There are some things it does say. I haven't read the spec, by the way. I'm just winging it. But I think it depends pretty much on the device. So you should always read the data sheet. Does the device support it? Can you send a restart condition and so on? And yeah, that's as much as I can say. I don't know, Pip, if you have some more comments on that.
if you really want to learn I2C, the best device, the best slave. And by the way, we are not supposed to speak like master and slave anymore because of the new thing stuff. Yeah, I mean, every manufacturing has its own standard. They normally say like leader and follower, right? because of the new era, right? But it's a memory. When you are actually talking to an I2C device, you're always talking as a memory, right? So you remember that you have one bit that it's a read and write, and that's the one that it's indicating you what's the next operation for the on the bus, right? And normally you're going to see that, especially in some Chinese, devices, right? You can see that there's one address to read and there's a different address to write, right? But the only difference is just one bit, that it's the one that Frank was showing in the frame, right? That's what normally happens, and that's all the confusion, because you normally say, yeah, I'm talking to 0x40 device, but at the end you need to basically shift that address one position to the left, and that's the one that you're looking for, right? That's I believe that's the most common problem in the I2C when you're learning that, the address.
Yeah, it can be tricky, and sometimes you just need to read it again and again to find out what's actually going on. And I think right now, if there's no more questions, I think now it's actually a good time for Pepe, if we can do some signal analysis. And first of all, everyone who's joining on YouTube, watching us, thank you very much for, yeah, we are thinking about you and we wish you were here. So as Cynthia said, we're having these meetings every month, and please feel free to come along if it's not too far for you. So we're very happy that you're joining us. So right now, we have a demonstration, and I will hand this to Pepe. And while Pepe prepares, I will set up the sketch. And okay, I will hand over now in 2 minutes.
Can you guys see me? Okay, yeah, I can hear myself, so it's good. Yeah. Is it working? It's fine. Próxima vez me la traigo.
Hace rato había 10.
There you go, yeah.
I leave you to it.
Okay.
¿Necesitas ayuda con algo más? ¿Te pongo otra mesa?
No, creo que con eso está bien. Mira, y aquí hay, here's some clamps. So what we can do is basically just connect those clamps directly here. And I'm gonna need a cable. You can use, each one you want to. Yeah, that's a ground. It's the same. You can connect and we can just, there you go. And we need another one because this is ground, right? So this is connected to the other one, and this is one of the, I don't know if it's SDA or SEL, so we will need to connect the other one. You need another one? Yeah, there you go. There you go. And I'm probably gonna need this one. Nice. Okay, so is it working? So do we need to put the reset button maybe? Oh, there you go. So, okay, so you remember that we have all this set up, last meeting, and we have like 2 analyzers that are for a serial, for a UART communication. So what are we going to do is basically just change it to enable I2C. But first of all, I think I'm just going to disable it so we can see everything in analog. So there you go. And if it's working, right?
Yeah. Do we need to reset it?
Yeah, I think so. Yeah. I think this is the one. Yeah. You saw it, right? Oh. I'm probably gonna need. Oh, there you go. So welcome to the I2C world. It's just a mess, right? So this is what Frank was saying, about the clock. So here you have the analog world, and here you have the digital world, right? So it's like a totally big difference, right? So this is a clock line, and this is a data line, right? So here you can see the clock line, and here's the data line, right? So, yeah, please, and we need to enable an I2C analyzer. So you go here and say add an I2C.
So, but first, let's see. Okay, so this is data line, or this is clock, this is data.
Yeah. This is the same signal, but this is the analog, right? And this is the digital representation.
So yeah,
It's really bad. This one it's basically what Frank was explaining to you, that it's the capacitance, right? So I2C was actually designed to be, physical lines in the same board, right? When you are actually connecting something over wires, using wires to an external thing, you are technically violating the spec, right? Because it's not intended actually to go out of the board, right? As you can see, if you can see here, there's 0 volts, and it's never, getting into the 0 volt stage, right? So it's kind of the problem, right? But at the end, basically, what all the transistors and all the logic said, they're going to translate all these voltage levels to something like this. So it looks good, right? It doesn't look really that bad, but that's actually what is happening in the wires. Yep. One example that Frank mentioned that it's a variation is the SM bus. So I don't know, guys, if you know about SM bus at all. So probably you guys are really young and you don't remember the times when you have those computers with these, big mechanical switches that say, hey, Windows allow you to actually turn off your computer, right? So what's happening is that you don't want, the big Intel processor taking care of all the power, right, and reading all the buttons on your computer and stuff like that. So there's always a small microcontroller that can be inside of the same chip or can be outside, right? And the way that you communicated with the big processor is over I2C, but it's called SM bus. It's a small variation, right? So the small processor is actually, sensing the push button that you push when you turn on your computer, basically turn on all the power screen, and after that, the processor will boot up, and it will start communicating with the small MCU to tell you, okay, yeah. And the best way to interpret that is when you're powering off your computer, basically Windows or Mac or whatever, just turn off, and the last thing that the main processor does is basically just say, hey, small MCU, just power off the power supply. That's the thing. And it's always I2C. So there you go. Can you read these things? Yeah. What it's actually telling you is that you're trying to write to the address 3C, and you're actually receiving an acknowledge from the device, right? And sometimes when you play with Arduino in the past, there's a function that it's called, I think it's discovery mode or something like that, that is actually, sending one frame to all the possibilities, all the address possibilities, and whatever, whoever actually responds back to acknowledge, it will tell you that there's somebody in this particular address. So that's kind of the discovery works, right? So if you can just scroll to the right. So here is what is happening right now. It's telling you that you're writing and you receive an acknowledge from the LCD screen, right? The next thing that you're saying is that you're writing a 0, right? Whatever that means to the devices, you're writing a 0. And the next operation is that you have this directly with an acknowledge, right? So you keep writing all the time, all the time, all the time. And the key is that you're seeing that the clock line is always in low state between the transitions. That indicates you that it's talking exactly to the same device. It is not restarting the communication again. That's the biggest indicator of. No, the clock stretching is that you can have all these, for example, this transition 1 to 0, and it can stay, on 0 longer. You're not going to see a clock stretching here because we only have one device, and it's not really that fast, and the LCD is not actually needed the clock stretching. Mm-hmm. Yeah. You can see that especially in memories, right? That you have a big memory, and it will take some time after you tell it, I want to read the address 5. The memory itself needs some time to actually put the content of the address number 5 into the bus, right? Memories are super fast, right? But there's some devices that need some time to actually do whatever you're asking, right? So this is how I2C looks like in the bus, right? If you connect more devices, you're going to see always, the bus is going up and down, going up and down. And what it's tricky is that Frank doesn't have the pull-up resistors on SDA and SEA lines. And I think that's one of the reasons why it looks like a mess, right? Yeah. Yes.
But there's other problems. I guess lower resistors mean also that you have more current being drawn, the levels. So you're basically squashing your signal with lower resistors.
And you remember that there's like a bit rate that is normally 100 or 400 kilohertz. We can measure that directly in the clock line. So if you go and put the cursor here, it will actually tell you that, the time between 0 and 1 is 1.3 microseconds. So if you convert that, you're going to find that it's around 100K.
Just to see if you paid attention. What is this sequence of data which is sent? Why do we need that? The first few bytes that we are sending to the display. This is what happens when you switch on the Arduino. Yeah. The first is the address.
Yeah. There you go.
Yeah. So if you could go on the GitHub page of ESG, just Google Frank ESG GitHub, you will find the code there that actually carries out things. Mm-hmm. I also have it on my machine, but I think it's easier if you just Google Frank Zeta Zulu Echo Yankee Delta Alpha GitHub ESG. Just go into collaboration, collab in the code.
The first one.
And now, just there's only one folder. And the main file there is, I think...
This is the source code for the Arduino
this is just the example.
Yeah.
This is a header file, right? No, this is a header file. Just go to the source code. And the initialization sequence is basically this sequence of data. And it even explains, you probably can't see that on on YouTube, or even maybe we can make this a bit bigger, just Control plus, something like that.
AE.
And we should see exactly those bytes on the bus. So I wonder, we can maybe do a quick check, and you see what happens here is display off, the clock divider ratio, so there's a lot of configuration here.
Yep.
There's a multiplexer for the screen, offsets, and this one is the most important one, it's a charge pump. To generate the right voltage. Sorry, let's just switch this. I think the battery is dead. Maybe Pippa, you could try and relate this to your signal output.
Yep. First one is AE D5, so we can just jump back to the other one. So we're talking to the address AC 0, right? AE. You remember that this is the first one that we were talking about, right? The next one is D5, I believe it was correct, right? So basically we are like, starting from address 0, we are just doing a consecutive write every time, right? Until we just tell the bus, okay, I'm done, right? Let's just restart again.
And all of this code is very easy to write with Arduino. So if you scroll down, so this is very easy to do with the wiring library. So if you scroll down a bit and you look at the code, all these functions are very simple. And
It's
this is
400K.
it just sets the parameters of the bus.
Yeah.
And then it calls a generic function for writing, I think, which I can't read myself, send, I think it's called. And if you scroll a bit further down, trying to find that send function.
P, yeah, there you
Send
go.
P. So it's send P because it reads data from program memory, from flash.
There we go.
And
This is one.
this is where you interact with the wiring library at that point. Now, the wiring library is your API to use I2C. You don't need to directly write to registers and have this low-level interaction.
You're
and
missing the fun part there.
Yeah,
so.
that's, you don't have to do the fun part. But I mean, this is fun as well in some ways.
Yeah.
So you're basically putting the write function there puts things into a buffer. Your buffer is 32 bytes. And when you're finished, you can end the transmission. And then you just say, no, send everything. So this basically is how easy it is to implement it. And I would really encourage you, if you want to write something like this, because this is an application level driver. You have at least two hierarchies. You have your device I2C driver, which is generic. Then you might have a driver for a particular chip. And then you have another layer for your application. For instance, if you have a game or you want to have some text. So this, I would say, second layer of that. So it might be useful if you want to implement something, just to look at that piece of code that will tell you something.
Yep. And another most common error that we as developer has is that we basically swap SDA and SEL lines, right? That's kind of the most common issue, right? And if you're using something different to Arduino, let's say probably a Raspberry Pi or another device, if your communication is not working, the first thing to check is actually using a multimeter to see if you have an idle state. You need to actually see that you have voltage on the lines. Yeah. Otherwise, that means that you don't have a pull-up resistors, right? That's also a very common issue. So it is not easy, but just like Fran said, once you write your own first driver, it's done. I mean, everything works the same thing. It's getting a little bit more complicated when you have multiple masters, right? But it's not really that common, honestly speaking. Oh yeah, I mean, you can use the analyzer. Basically, this is how it looks when you're swapping the lines, right?
You don't break the chip by doing that. That's a good thing about is that you can swap the lines.
Yeah.
Your device will not work. So I think this is really useful and really helpful. I think we might maybe take a short break because Carlos. And one thing we cannot do today is to try. So first of all, thanks very much, Pepe. that gives so much insight how this works, and that's fantastic. So I would say we take a short break, maybe just 10 minutes, so Carlos can set up. Unfortunately, we are not going to have the workshop today because I think we are running a bit out of time, and we can continue this another time. One thing I would ask you guys is, so I'm thinking, I also asked Pepe about this, to have on the 16th of December a vintage gaming event. And it's going to be a Saturday. It's going to be before Christmas. Actually, Cynthia recommended we do it on a Saturday. It might start at 10 o'clock and go till maybe 2 or 3, I don't know. And we have a mixture of talks and games. Vintage games, no? So you can bring your favorite console. I might talk a bit about the Mista, which is an FPGA-based gaming system. Maybe we can coax Pepe into giving a talk as well. Yeah. Yeah. So when we talk about vintage gaming, we are not talking about PlayStation 1. So we're basically talking about Atari 2600, you know, the old arcade boards, the PCBs. And I really love that stuff because you see the whole history of computing reflected in that. Also emulation, maybe we have some modern emulators. So we will talk about this. Speakers would be very welcome. So any one of you likes to give a talk about the Atari 26, you know, how the hardware worked, how the games worked. There's a lot of information, and yeah, exactly. Yeah. Yeah, so that is the plan, and we will announce it on the WhatsApp page. If you're not on the WhatsApp page, let me know. We can do that, so that's the plan for the rest of the year. So we take a short break for Carlos, and then we have another half an hour, 20 minutes, and then maybe have a few beers if you like to join us. Cool.
Este sí se oye bien, pero como que el otro no.
Tienen una opción de que si les escuchas una vez, se mutea. ¿Sí?
It's so the second talk we have today, or actually the third one because we already had 2 talks, is given by Juan Carlos Arias.
Yeah.
And Juan is a freelancer and a multi-talent, I think. You told me about many things you were doing, so I'm assuming that. And he very kindly offered to show us a bit more about I2C, not using the Arduino, but using a Pico, a Raspberry Pi Pico. So Raspberry Pi recently got into the business of doing proper microcontrollers. A Raspberry Pi is not a microcontroller, it's a mini computer. And it will be very interesting to see what language and how you do this. So thanks very much. Thanks very much, Carlos. And
Sure. So first I want to start by saying that, so Raspberry Pi is known as a microcomputer, but Raspberry Pi Pico is a microcontroller. That's like the difference. You are more limited. So you can see this is very small chip. Is actually the Raspberry Pi Pico compatible because it has the RP2040 chip. So I can turn it on. And I have some demo in here. So you can pass it around because it got battery and everything. So it's like a joystick, and you can like select an icon. So it's showing us how to display text and also how to display graphics. I have worked a lot in as a front-end engineer, so that's my current work. That's something that I've been doing for 18 years. So I have gone like through a lot of changes in the web, which means that you went from a lot of limitations, like I was doing Flash at some point, and I was doing, responsive design before the term was even coined. So that's how I know how to do a lot of UX, UI, how to do a lot of tricks, because I was limited in memory, because right now JavaScript is very powerful, but at that time it was not. So let me present this. So we're going to talk a little bit about how to do a driver, because not always you will have something, or not always what you have is what you actually will be needing. So the first rule is get to know the enemy, get to know the driver, get to know what are the tools that you're using, knowing the protocol, knowing the chip, knowing the capabilities, knowing how it works. Because if you don't know it, you don't know how to pull a lot of tricks. So for example, this is how you pull icons. So you can see here, this is an icon, and it's divided, it's a 16 by 16 pixels icon. And what I'm doing here is showing you what exactly is transferred this into the screen. So this byte is the first one, is the least actually most valuable byte. So it's the one on the very left. So that's 0, 0, 1, 1, 1, 0, 1, 0, which is 0x3a. So whenever you're trying to draw an image into the screen, you're using like 8 bits, 8 bits, 8 bits, 8 bits, 8 bits, because it's 8 pixels, because each pixel is going to be either a 0 or a 1. Now, this is only valid for this kind of display, because this is a monochrome display. There are like displays that use RGB, so that's 3 bytes per pixel. There are also black and white displays with 4 bits per pixel. So depending on your display is how you're gonna be doing this kind of calculation to do some memory manipulation. Now, there's a lot of tricks that you can do today, because you might be asking yourself like, oh, I want to do a video game, or I want to do a graphic. And well, you can search over the internet, but what happens if you don't find it? Well, at this point, you can actually use ChatGPT to generate some of the icons, some of the graphics. You can use it to generate monochrome images. So the problem with libraries that you will have available is that they come with a lot of baggage. They come with a lot of assumptions. You don't know exactly what they're thinking and how they calculate it. A lot of these libraries are used for multiple kinds of displays. So they are trying to do multi-purpose, and that happens in coding with everything. Like if you talk about React, about Angular, about every single framework, it has a lot of assumptions, and those assumptions are gonna cost you. In computers, it doesn't matter that much, but since we are on the microcontroller side, you got limited memory, limited capacity, limited power. So for example, this is the code for C, for the Adafruit, GFX, which actually is the one that uses for the Adafruit SDD130806, which is the monochrome screen. What is the problem with this library? I don't know if anyone can spot it. There's a reason why this library is slow. Not so bad, there's actually worse things. It's this part, right pixel. So remember the last image, we were writing 8 pixels at the same time, and here we're writing one of them. So for writing a single column, you're gonna be calling this function 8 times instead of a single one. So we gotta use our limitations in favor. There is this artist, who is already dead, Dali, which was talking about creativity is something that happens when you get into limitations. So for example, if you are on a monochrome screen, you cannot use more than a single color. So that can play in your favor. How do you express an icon? How do you express an image? How do you express something with those kind of limitations? And that's when you start seeking for some creative solutions that you will not be able to seek if you have like a full OLED screen with very giant and having everything on your side. So also one thing that you need to be thinking about is try to avoid conflict. Like you see the library can only write 1 pixel at a time, and instead of trying to battle against it, you start to know the library, know what it's capable of, and extend it or use whatever you need to be using, but ignoring the rest, so that therefore you can take advantage. You are not going to rewrite the driver, but you are going to extend it. So I don't know if someone wants to take a scan in the code, because this is actually going to contain a lot of examples. So I'm using this software, well, this page called Walkway, in which I can actually simulate the actual Raspberry Pi Pico in here, and I have this screen in here. So for example, I can hit play, and you can see that the screen is going on. Let me make this bigger. Let me do it again. So you can see we have a problem in here. So these kind of libraries that we saw are being used. You can write text, yeah, super nice. But whenever you write text, it doesn't erase the previous text. So you get into this kind of problem. So very simple. Let me see if I can make the code bigger. Is that better? So for example, this library, so this is actually MicroPython. This device actually uses CircuitPython. So it's a variation of Python, very similar, but it's like a small subset. So the actual library has a lot of functions in here, like we can see. Take a look at it. So the problem here is that every single frame, we're just writing to the screen, and we are writing and writing and writing and writing. But we are never erasing the screen. That's why you can see that instead of actually being able to see the value in here, every time it keeps overlapping, and therefore at some point it's just gonna fill the entire square. So all that we need to do in here is search for what is the function to clear. Oh, this is the initialization sequence that was presented before, but this one is actually in MicroPython. So, oh, I know why it's not showing here. It's because this is actually inherit from a frame buffer. So that's why the function won't be in there, but it's this one. Or maybe it was not. Oh, yeah, I see. So there wasn't a clear method, now I see, because I had previously coded in here. So for you to clear the screen, you can just fill it with 0. That's all you need to do. So like I was saying, you can just extend whatever is available in there. And now you can see. Now we're able to reset the screen on every single frame, and now we can actually get the time value being updated. This is like a frame per second like graphics so that we can track how fast are we going on the speed. Now, this kind of simulator is pretty good because it's kind of accurate. So if you try to run this in this device, you will actually get that kind of frame rate. Now, one thing that's interesting is that here you can actually define your bus rate. Let me try to make that bigger so it's easier to be read. Okay. Okay, so you can see right now is 400K. So we can change that to maybe 800. And you can see it goes a lot faster. But actually, it's not the double. So it must be something related to the actual hardware. Like you can, I think you can use over 1.2 something megahertz, but you won't get that multiplication that you're actually expecting, probably due to the physical limitations of the protocol. So let me jump to another example. So here we're doing a little bit different. So I already took care of making sure that we are not erasing the buffer every single time. So what I end up doing in this example is whenever I'm printing text, I'm actually going to set up like a virtual cursor. So we have our x coordinate. That's always the x coordinate because we're running 8 pixels at a time. So that matches perfectly. But the y, the row, is different because every single row is 8 pixels. So that's why I'm dividing by 8. I know it's not so very readable, but this is divided by 8. And now this double slash is going to be like a math floor. So it's instead of just dividing by 8 and getting like 3.5, you're going to get just 3. So I do that, and then I start running this while loop. I calculate where is the start of the text, the end of the text, and then I'm just going through every single one of those bytes and actually setting a 0, 0 so that I can erase it. And that helps me not having to reset the whole screen. I'm just resetting this part of the screen that is changing, which is the text. Every single time I'm just rewriting it. So therefore, I prevent having to rewrite the whole screen to 0. And that will help me, like, if I want to do some complex graphics, and I know, like, if I'm trying to pull off some kind of video game, and I don't need to rewrite the entire screen, that will make it have a higher frame rate. I don't know if people know this very old game called Sokoban. It was like very old. It was like from 90s, I guess, something like that. It was like a maze that has a lot of blocks, and then you have boxes, and then you have your character, and that character was like pushing the boxes, and you have like a target to where to push the box, so it was like kind of a puzzle game. The thing with this kind of game is that you don't need to write everything on every single frame, because the only things that are moving are the character and the box that you're pushing. So therefore, using this kind of methodology, you can get higher frame rate because The only thing that you need to do is taking care that making sure that you are erasing the character, erasing the box, and then rewriting it with the new position of the character and box. Now, let me go to next example. So I'm trying to build like what you saw in this device, but I'm going over different stages to show you a little bit of the process. So this one, I went like from nothing to something more complicated. And here I'm already integrating the images. Now, this is a little bit different because, like I say, this is using MicroPython, and the other one was what you're using in the device is CircuitPython. Now, a difference between CircuitPython and MicroPython is that when you don't implement the library or you don't implement your own functions, you are using whatever is available from there. And what is available for MicroPython is you need to define this kind of byte arrays, and then you need to get it into this frame buffer. Now, the difference is that if you remember how I was doing it, it was 8 pixels at a time, 8 pixels, 8 pixels, and 8 pixels. But when you're using this kind of frame buffer, you're going on rows. So it's 8 pixels like this, and then the next 8 pixels, and then the next row, 8, and 8, and 8, and 8. So that's why you gotta know exactly how things work, because if not, you're gonna make the incorrect assumption, which I actually did in this example before when it was not working and it was just messing up the graphics. But it was just because of that. Now you can see that at this point the rate is still pretty high, 33, 34 frames per second. This example is running at 400 kilohertz. So it's not running at the 800 that I showed you previously. So it's still quite good. Now this example is a bit different. Now here is the problem. So in this one I'm using, and all the previous example that you saw, I'm using the library methods that you have for printing text. So if you want to print text, you have only 16 characters available, which is like very small. If you want to write just like a few words, you will have problems trying to write that. And what I was doing here was also erasing the next column. So one thing that happens with the print text for this kind of things is that all the text that, like I was trying to print 21 characters. So what happens is that all the rest of the characters that could not be printed are just simply ignored. And my function was calculating like the next pixels are going to be erased, and that's why you can see that this part of the image is actually being cut. So that's why I say if you need to learn exactly what are the limitations, because if not, you will get like some of these unexpected results, and you don't know like exactly what has gone wrong. Now, let me actually pause that. Yeah. Yeah, this actually is already, I think this one, let me see. No, I think that's the final example. Yeah, so you can see here I have my draw text. So I'm going through the cursor, and then like this is the tricky part because you are going to, I'm trying to avoid doing what the Adafruit library was doing, which was printing pixel per pixel per pixel. And that is, I guess the reason they try to do it that way is, first of all, that library is used for also displays that have 1 pixel. It's 3 bytes because it's an RGB. So it makes sense at that point, but therefore you're not taking the advantage. But also what happens when you break into multiple lines, because right now I'm very happy because I go 8 pixels and I'm using from 1 single row, and I can just print them one by one, and that's simple. So this is that happy path of not having to do that kind of like, I just, for printing a character is 5 columns, so you can see 1, 2, 3, 4, 5, it's 5 pixels, boom, you're done. That's simple. But what happens if instead of you want to print from on on x equals 0, on y equals 0, you want to print on y equals 4. You're going to have half of the character on the first row and half of the character on the second row. But in this example, you can also see how you deal with that. So I know it's a little bit more complex, but that's what happens when you're trying to do this kind of things. Like if you use the regular library, you're just taking the fact that it's just going to be working. And if you're coding like in JavaScript for the web browser, all these things are like, oh, just print the text and you don't need to deal how you're going to structure your UI or anything else because everything is just taken care. Whenever you're doing and dealing with microcontrollers, you need to do everything by yourself. Basically, you cannot take anything for granted. So for example, even this part, when I was doing some experimentation, I was just getting like raw text from ChatGPT and just pushing it into the display. But some of the characters were invalid. So therefore, I need to take care of checking that the character is actually one that I had at my table. So the table that I have for characters is this one. So it's just a huge array, very big array that contains all the pixels for every single character. And even getting this was a little bit tricky because I was just trying to do the byte array like I did for the images, kind of this format. But I was not able to get it to work that way because I was getting error on the microcontroller. So therefore, I needed to parse it into this kind of syntax that you see it's a little bit different, which is with the B instead of the other one that looks more like an array. And this actually is being able to be written into the microcontroller. The other one was not able to. It was just given error. Now, you don't get like very useful errors on these microcontrollers. You just get like, it doesn't work on most cases. So you feel like this was like coding for the web in 2005. You basically said, doesn't work, that's it. Now, this is the next example. However, I also want to show this, that if I click the buttons, it's going to go to the next icon. And now you can see I'm using like all the power that you see in the device in here, but I'm using different strategies. So before, what I was doing is printing every single of the icons every single time. Now what I'm just doing is just printing these values up here and updating the frames per second graph. But this one, I'm just using and keeping whatever was in there. So whenever I click the button, I'm just overriding the icons and overriding that part. But that's the only case that I'm overriding that part. And you can see that there's a huge difference on the frames per second that I'm getting just by taking advantage of not having to rewrite the whole screen. Now, this screen is always being sent like I'm keeping this on a buffer, so every single frame, I'm sending the entire set of all the pixels. However, I'm not recreating all the set of the pixels. So that's the difference, and that's why this one is a lot faster. And yeah, that's the examples that I have. Yeah. It's a little bit different because that one is MicroPython and this is CircuitPython. But this is CircuitPython because like I'm working on a project of doing like a macropath because I just wanted to do something that I'm able just to click and have like some shortcuts from VS Code. But when I was building that, I just learned the shortcuts and then it's like I don't no longer need the macropath.
Cool. Anyone?
Have you played with, it's not more capable microcontroller, but with a different display that it has more graphic capabilities, like RGB stuff and
Yeah.
full frame buffer and all that stuff? And what kind of libraries do you use for that?
I found one on the internet, but again, I changed the,
Okay.
the functions in there. Yeah, so I was trying to print icons, but then like I stopped working on that because I was just obsessed on trying to build a macro pad.
That's nice,
And
yeah.
for the macro pad, I use this kind of OLED screen because I don't know if you have searched like some nice keyboards. They use like a little OLED monochrome screen. So I actually wanted to have like some kind of animation when I press a letter. And I told ChatGPT, because I wanted like a cat, an Egyptian cat, and I told him like, make me an Egyptian cat with 3 eyes, and it made me the image, and then I just modified what I was getting from ChatGPT, because it's not exactly like a grid pixel perfect thing. Yeah. And then I put that into Figma, and then I translated, and then I put it into the OLED screen.
I saw a project that one guy was using multiple of these OLED displays, and they were building like this stream deck kind of device, the one that you use for streaming things or you know, shortcuts and all that stuff. And it's pretty cool. But the thing is that it requires a lot of bandwidth on the I2C, you know, on the I2C bus, but looks amazing. And it's really nice. And each one of the screens is actually a physical button. So
Yeah.
it's really nice.
There's a lot of screens, like there's like touch screens that you're able to buy, which are not like very expensive. But what I like about OLED screen is like the contrast that it has. Like it's really cool. The black is really black, and the white is like so bright.
Yep.
And so when I was doing my experimentation with the color screen, I was able to print some icons like coffee, because I was kind of just doing like food themed stuff. But I didn't like how the black looks, so I just go back to the monochrome screen. But I guess that's just a preference that I had for how it looks.
The icon looks really impressive. I really like them. I mean, having all these things, you know, and you're allowed to actually recognize them on a very low resolution, it's just fantastic.
Yeah.
Congrats, yeah.
So you mentioned that you had the entire screen buffered. Is that what I heard? So you have a big buffer of the entire screen. So now that you're repainting, are you repainting only the difference of pixels between the previous buffer and the new buffer, so you have double buffer or something like that?
Yeah, let me show you the coding here. So here is the trick. So I'm checking if the, so I created another class for dealing with buttons. And so I can just get the buttons and call the function update. And it's just going to throw me different states of it. So if I have like a single press or I have a long press, so for example, I can just leave the blue button press. And you can see it keeps changing. So whenever there's an update in there, then I say like throw icons, and then it's going to throw all the icons. And that's it.
Okay, thanks.
I might have one, one more.
Okay.
So I think when you use a frame buffer, there's like two ways to interact with the system, right? With your data. So you're writing things in the frame buffer, and then the frame buffer needs to be sent to the display. Now, I know the Pico is much more powerful than the Arduino, so it uses things like DMA. And I would think that the Pico also has built-in I2C controllers, I think.
Yeah.
Do you know if this library uses any of these controllers to, or uses DMA to send the data to the screen? Or is it something that's not really transparent in the code?
So you use the I2C protocol in here. So you can use that class, and therefore you're just able to get the, and then to the library, you just send the connection to the I2C.
So it's basically happening inside that class, the transfer.
Exactly. So that's kind of the library that you're able to download, this one. And then the rest is like I'm just trying to deal with how to manage with edge cases or what I'm trying to achieve in here, which is like not trying to repaint everything every single time.
And you mentioned that this is much slower than writing native C, right?
Yeah.
And this is a very interesting issue because when you design drivers, you always want to make sure they're mostly working without the CPU. So everything should be interrupt driven, and you're just feeding your hardware when you need to. And DMA is a very good thing for that because DMA is something that can feed the data, and basically you only generate an interrupt when your data is sent to the system. So it would be nice to see if something like this happens inside there. But I guess because this happens probably, I don't know, in the library implementation, it's not so easy to see it in that code because it's all encapsulated. But
yeah, that's kind of the problem with all libraries. Like, doesn't matter the language or the environment. Like, there are things that are simply hidden from you, which is good in some ways, but it's also bad when you want to take things to the extreme or the next level. I have seen, I don't know if people have seen like projects like the Arduboy. There are like some like small consoles that people trying to be building around Arduino or the I2C Tiny, which is another chip. And some of them use this display, actually most of them use this display. And because they are achieving like a very high frame rate, they are able to pull out like grays in the middle. So by flashing it, boom, 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 you can get like fully on is white. And then on, off, on, off, it's a certain color of gray. And I have seen people pull out like 2 different gradients of gray and white. So
it's like a PWM signal you're sending to the screen. I know when I first had an Amiga, then people managed to slowly dim the power light, which wasn't possible in hardware. So, but it's very interesting. It's nice to see that you can simulate. I mean, a Pico is not a simple chip. I mean, and this simulator basically is quite accurate, right? And quite fast.
Yeah, it's actually better for Arduino. So if you're trying to simulate Arduino, it's actually better. You get like if there's kind of a bug, you get something better than what you get from the simulator when it's Raspberry Pico. Also for Raspberry Pico, the support is like very recent. So I hope that it just gets better in the future. But right now, this is what we currently have, which is good.
Yeah, looks very good. So thanks again very much for the talk. So one more request is if you can upload this onto the GitHub page, that would be really cool so we can look at it. And I just passed to Cynthia. I think we are done with the ESG now. So thanks again very much.
Any other announcements?
No, I mean, my only announcement would be for our social. One thing I think that we need is sponsors. So anyone in the room, if you're watching online, YouTube, and you'd like to sponsor some of our events, that would be really appreciated, both for the group and also for Hacker Garage. So it makes this incredible effort that the staff here, Cynthia, is doing much more worth. So yeah, please come forward. We still need to find those. And yeah, thanks very much for joining, and join our Meetup site, join WhatsApp. And I'm going to hand over to Cynthia for the finish.
Okay, muchas gracias. Thank you so much. It was an amazing talk. I'm really, really glad that we did this and that we get to share it with the people online. I think this is a major thing for Hacker Garage and for the community. So thank you so much for all of you. And now that's it. Now we can get together and continue talking. And thank you so much. Welcome to Hacker Garage.